Okay, what questions do we have this morning?
Could we look at number 26?
Sure. Okay, so we're integrating the speed. So the function f is the velocity function, and we're supposed to average 27 miles per hour. So the integral should give us the total distance, and well, we're integrating with respect to distance actually. So f of x isn't the velocity function. It's like it's a 1 over t function, which doesn't make much sense, but you'd be integrating over the 162 because that's the total length of the trip. So you're going to go from 162 to 162. And this is 1 over b minus a, from a to b of the function. And that's going to give you your average. So the average is going to go in at the end, but you get the integral divided by the length of the domain of the integral, or the yeah, I guess that's kind of the domain of the integral. Can't think of a better vocabulary word for it, so we'll call it that. But you're going from 0 to 162. That's how far the trip is. Your trip starts at 0 miles and ends at 162 miles. So you're going to divide by the length of the trip outside for your average function. It's going to go up to here, and you're going to get this. But it doesn't like that. Okay. Oh, okay. So it does want f to be the velocity function. So 162 miles at 27 miles per hour, how long does that take us? Well, it takes us 6 hours. So we're going to put the 6 hours in there and the 6 hours in here. That's what it wants, not integrating by miles. You could have been integrating by miles and your function would have been really funky, but if it wants you to integrate the velocity function, which it doesn't really say, I'd set it up this way. Okay, so the reason it's 6 is because if you're going to go 162 miles at 27 miles an hour on average, it's going to take you 6 hours to do it. Does that make sense? On this one, the back half of the trip only takes us 2 hours, but apparently I would assume that it wants us to start after we stopped the first trip. So from 6 to 8 would be those 2 hours. And then we're going to get 81 because I assume this is still the same function f. And it looks like we probably just went there, turned around immediately and came back. So we're going to assume that 6 and 8, because it should be the same. The 0 to 2 values for x's in here would be different. So let's check that. Okay. And then, so we're going 6 hours at 27 miles an hour and 2 hours at 81 miles an hour. So basically we went, if you do all that, you could do it with a weighted average type thing, or you could just realize that you went 324 miles in 8 hours. So that's 320.4 divided by 8 would be 40.5 miles an hour. So you just add up the total distance and divide it by the total time, then you get 40.5. Well, the time that you're traveling around 27 miles an hour is longer, so the weight of that value in the average is heavier. So the average should be pulled towards that value more than it should be towards the 81 value. You're only spending 2 hours going really fast, but you're spending about 6 hours going pretty slow. So your average value is going to be closer to 27 than it is to 81, which we see, right? It's half of 81, but it's only like, well, it's 50% smaller than 81, but it's 50% bigger than it is than 27. So it's like right in the middle there. But absolute value wise, 13.5 is the distance from 27, and 40.5 is the distance from 81. We'll go with A. Okay. Did that help with that one?
Yeah, thank you.
Okay. Other questions you guys have? Okay. Right. So we've got the circle of radius 3, which is the back half of this, plus 4. So we're going to go this guy, basically. So I have to go 4 and then up another 3. So that gets me up to 7 at the top. So I've got the circle, but it's lifted by 4 is what that is. Square root part gives you the circle. The plus 4 just shifts it up. Okay, so geometrically, how would I find this area? Well, I would find the area under the circle, in sense that like completely under the circle, just this rectangle, this 4 by 6 rectangle, that's 24. So it's going to be 24 plus the area of half the circle. And it's a radius 3 circle, so it's going to be 3 squared times pi over 2. So it's going to be 24 plus 9/2 pi. Does that make sense? Yeah. Other questions you guys want to talk about? Yeah. Use the equation to evaluate. Yeah, you can set it up, and then this is a lot like the 5.2 problems, but if you want to just use what we did yesterday, that's fine too. Yeah, so this will be, let's just do this. So what it wants you to do is use the, what is that? That's the right hand rule. So it wants you to take Okay. F is the square function, so 7. A is -3. Plus K times B minus A is 3 over N. That's the 7-bit -6. We want that whole thing squared, so -3 plus 3K over N squared times 3 over N. And it wants us to sum up that whole thing. So you'd split it up into different parts and add up each of the parts, with the K value being the last thing inside and the K squared value being the last thing inside. But this one, you're going to have to distribute and all that. So we could do it like we did last time, but we already have the sort of rules for some of this stuff. So -3 to 0 of 7x minus 6x squared dx. We know that's 7 times the integral of -3 to 0 of x dx minus 6 integral -3 to 0 of x squared dx, which is 7 times 0 squared minus -3 squared over 2 minus 6 times 0 cubed minus -3 cubed over 3. That's 9 halves, 63 halves, minus, well, there I've got a negative, I got 4 negatives there, so that's a positive. There's a 5th negative, which makes it negative again. So it stays negative. It's a 27 over 3, which is 9, and 9 times 6, which is 54. So that's going to be 63 minus 108 over 2. 45 over 2. That's what we should get. If I did my arithmetic right. That's not what I did. Oh, it's still negative there, yeah. So minus 1 81. No, 71. Minus 171. Try that. There we go. I would just do it that way. You did the other way, probably. And it's good to know the other way, but sometimes those get a little tedious. And we have better ways to do that at times here. Let's see. Number 18. So we want t minus 4 squared. So it's going to be an upside down. No, it's going to be a right side up parabola shifted to the right by 4. So that looks like this guy. How do I know it shifted better? Right by 4, because if I put 4 in, I get 0 out. So it should have its vertex here at 4, 0. So let's check that. Okay. And we want to find the average value here on the interval from 0 to 9. So I want to find the area under that and then divide it by 9. So the average value of f from 0 to 9, we'll write it that way. That's going to be 1 over 9 minus 0, integral 0 to 9, f of x, which is t minus 4 squared dx. Okay, I'm going to do a little bit of weird geometry here because I don't want to have to expand that out and then deal with all three things. So if I notice, this is the same geometry as if I'd shift this back to the center at 0, right? So right now I've got this function, and it starts at 0 and it ends at 9. And if I shift it back to 0, what's that shift my bounds to? It shifts them to -4 and it shifts them to 5, right? So if I find the average value of the green function, that should give me the same as the average value of the white function. We all good with that? So instead of having to deal with this -4 expanded bit, I'm going to go, it's the same thing as the integral from -4 to 5. And I still have 1/9 because the interval's length stays the same. But now I'm just looking at t squared dt because I've unshifted it. Okay. That's just going to make things easier because we know exactly how to evaluate that integral. That integral is 1/9, and then I've got the 5 cubed minus -4 cubed over 3. So that's going to be 125 plus 64 over 27. So that's going to be 189 over 27. And those are both divisible by 9. That's 21 over 3. That's actually divisible by 27. Okay, so that's 7. So my average value over that's going to be 7.
How did you know to use -4 and 5?
So when I talked about this shifting over, the vertex here was at, the vertex on the original graph was at 4. And I want to bring that back 4. So maybe I should regraph this. This is where 5 is. But the vertex here was at 4. So to shift it, I had to move everything to the left by 4. So 9 to the left by 4 moves to 5. 0 to the left by 4 moves to -4. Is that?
Yeah, I think that helps.
And I knew the vertex was at 4 because this was originally shifted to the right by 4. Like f of x minus c, that's a shift in the graph to the right by c, right? Okay, so we just undid the shift of the -4 and the squaring function. You can do it by expanding it out and then doing each of the pieces too. It just, this was a little shorter. Should we do it by expanding it out?
No, that's all right.
Okay. Other questions we have today? Oh, so one of the things we wrote down the other day was that if you find the maximum value over the interval and then you take it, so the picture is you've got a function and you want to find the area under the curve. it's at least as big as that rectangle, and it's at most as big as that rectangle. That's the max min thing. Does that make sense? So I find the minimum function value, turn it into a rectangle. That's an area that is smaller than the area under the curve. Find the maximum value. That's a big rectangle that's bigger than the area under the curve. So the area under the curve has to be between those two more. So on this one, we're looking at 1 over 1 plus x squared on the interval from 0 to 1. And this is going to be as big as possible when the denominator is as small as possible. So it's going to be as big as possible when the denominator has an x equals 0 in there, which is at 1. And it's going to be as small as possible when the denominator is as big as possible. So it's going to be as small as possible over here, which is at 1/1/2. So this function kind of looks like this, kind of. And so the minimum value that I would get is, because the minimum value is 1/2, the area is at least 1/2. And it's at most 1, because my maximum value is 1. This rectangle would have an area of 1. So upper bound 1, lower bound 1/2. Other questions we have? Drawing pictures is going to be helpful on this stuff. Really helpful. Okay. I'll start talking about some 5.4 stuff then. Okay, so the first thing in 5.4 is the mean value theorem for integrals. So let's talk about what the mean value theorem for not integrals actually said, right? So the mean value theorem says if I have a function that starts at A and ends at B, then there's this secant line, right? And the secant line actually matches the slope at least one place on the graph, right? If the graph is continuous on the entire thing, then there is some place where the secant line for the graph matches the derivative for the graph. So if f of x is continuous on the whole interval, differentiable on the interior, then there is some c in AB with f prime of c equal to f of b minus f of a over b minus a, right? Well, we're going to take this to integral land. And integral land says that if f is continuous, on AB, then there is some C with f of C equal to 1 over b minus a integral a to b f of x dx. Okay, why is that? Well, if I think of this function here as like capital F, we're going to go a to x f of x dx, right? So what's going on with this picture then is here's A, here's B, here's this thing, and then X is somewhere in the middle. And f of x is going to be the area from A up to X. So as I move X a little bit to the right, this will be, say, delta X to the right. The area that gets added, this is f of x plus delta x minus f of x. Right? And so the average value of what is added would be the height, basically, of this extra rectangle that gets added. Is that green hard to see? So that's the average value of the rectangle, which is basically the height of the rectangle. Okay. And then the limit as delta x goes to 0 of this thing, f of x plus delta x minus f of x over delta x. This is the limit of the heights of rectangles as their widths go to 0. Does that make sense? Okay, so if this width is going towards 0, what's the height of this rectangle approaching? It'd be approaching whatever this point is here, right? Because this function was continuous. So as these rectangles get close here, this point at x comma f of x, because that's what I was integrating, was the f of x function. This is going to equal f of x. This is also the derivative. That's the definition of derivative for f of x. Right? You take x, you add a little bit to it, you apply it to the function, you take the function at x, you take the difference. This is the change in the y value divided by the change in the x value as x goes to 0. So this is the derivative of capital F, but geometry also tells me that it's little f. Okay. So we just proved that this integral function basically has a derivative of little f inside of it. So if you integrate a function and then take the derivative, you get the function that you started with before you integrated. Okay. And so that's what's going on here is I'm thinking of the mean value theorem, only the function that I'm using the mean value theorem is this guy, right? So if I take f of b minus f of a, which is this full area, right? So f of a to a is 0. So really, this whole thing would just be, this would be f of b minus f of a, which is equal to 0 in this case. This bit's equal to 0. You just get f of b divided by b minus a is equal to the derivative of the function that I was differentiating. So that's why this thing's called the mean value theorem for integration, because it is just the mean value theorem. But the idea is all in this geometry here, where we define this nice function that we can differentiate and get the original function back out of. And that's basically the entire proof of the fundamental theorem of calculus, which says that if, say, f of x equals the integral from 0 to x, little f of x, let's go t. So I don't have those guys floating around with different x's. So I'm going to integrate with respect to t, little f of t, and then I'm going to evaluate at 0 on x. And that's a function f. Then little f of x is equal to f prime at x. That's the fundamental theorem of calculus part 1. Let's write it out the first time. And there are some restrictions, right? I think I want little f to be continuous. Yeah, I need little f to be continuous. So if f is continuous, then if we define it that way, we're good. Okay. Let me write it out explicitly with all the bells and whistles. So if f is continuous on AB, then f of x equal to the integral from a to x f of t dt is continuous on AB and differentiable on AB with f prime at x equal to little f at x. I.e. f of x equals d dx of the integral from 0 to x f of x, let's go f of t dt. So differentiation undoes integration. That's what that one says. Yeah. So they're kind of different variables in some sense. They're on the same axis, so I'm thinking of this as an input into the integration. So it's one of the bounds on integration. T I'm thinking of as input into the function f. So they're still horizontal axis values. This one just tells me where do I evaluate the function f, but this one tells me where do I stop evaluating the function f. So for this one, because I'm integrating, I have to evaluate this t value for every value between 0 and x. But x tells me where to stop evaluating them. It's a little weird. Mostly, you're just trying not to confuse where the variables are. If you actually write down functions and stuff, it's nice to have a different variable inside the function, inside the integration, so that when you evaluate, you know specifically where you're going to plug stuff in. Because a lot of times this isn't just an x. Maybe this is like an x squared plus 1 or something up here. And then if you have x's down here and you're halfway through plugging stuff in, you've already plugged in some x's, but you've got other x's you have to turn into x squareds plus 1s. And then it just kind of maybe gets messy. Does that make sense? It's kind of an organizational thing to keep track of where stuff is. So I am evaluating each of these guys at t, but where I stop evaluating is at x. So let's draw a picture. This is f of t, this is the t-axis. I'm going to tell you where to stop, and a is where you start, right? Okay. So if I told you to stop at 3, you would be able to tell me a fixed value, right? The f of 3 would be this area right here. Right. For each different stopping point, you get a different area. So f of x equal to the integral from 0 to x f of t dt. This is the area under f of t from 0 to x. Maybe that's 0. Well, that area depends on where I stop, but it doesn't depend. I mean, it does depend on the function, but it doesn't depend on what the variable in the function is. It just depends on where I stop. Does that? Okay. Okay, so the second part is now we're going to sort of undo some of that. So we've got this relationship between if you integrate and then you differentiate, you get back to where you started, right? And so the idea is if I differentiate and then I integrate, I should get back to where I started. So do them in either order and you end up where you started, okay, kind of deal. And so this is the fundamental theorem of calculus part 2. And that says if f is continuous on a b and f is any antiderivative then I should say for f on AB, meaning that the derivative of capital F is little f for every value in the interval. Then the integral from a to b of little f of t dt is equal to the antiderivative evaluated at each of the endpoints and then take the difference. And so you can find the area under a curve by finding an antiderivative and evaluating at the endpoint. Okay, so let's see an example of that. So I want to find the integral from 0 to pi of sine of x dx. So if I draw my picture, there's my sine curve. This is pi, this is 0. So I'm looking for the area under one lobe of the sine curve. So that's what this is. What is that? Well, what's an antiderivative for the sine function? The negative cosine. Okay. So the negative cosine of x, if I take the derivative of that, I get the sine function. So negative cosine of x is an antiderivative for the sine of x. So this area is minus cosine of pi minus cosine of 0, which is minus 1 minus 1, and that's a plus, so this is 2. So there's 2 under that lobe. Yeah. So if there's a constant in the antiderivative, you get the plus c here, but you also have a plus c here, which gets subtracted off. So no matter which constant you pick, because you're doing this difference here, the constant gets added on this side, it gets subtracted on this side, so it doesn't matter what constant it is. Yeah. Sort of the idea is you've got this function, little f of t, and you've got your capital F again set up as the integral from a to x, little f of t dt. Well, the constant is where I pick the starting value for your function like this. You pick a different a value, you get a different constant. That's kind of how that works. Right. If I picked A1 here, I'd get this area. If I picked A2, I'd get this area. But as x changes, this constant, this difference, this area here would be the difference in the constants between these two things. Okay. So sort of a corollary. If f is differentiable over a less than or equal to x less than or equal to b, then f of b minus f of a is equal to the integral from a to b of f prime of x dx t dt t dt. So if you put the derivative inside of an integral, then the antiderivative you choose is just the original function. And you can get that out of there. So like if I know the position function and I want to integrate the velocity, I can just evaluate the position function at 2 spots and get how much the velocity was integrated over that area type thing. Okay. Any last big boxes in here? Sort of a note or a warning. Integration gives the total signed area. i.e., if we integrate sine of t dt from 0 to 2 pi. Well, this is all symmetric, right? So this we measured to be +2. This would also be 2. So I'd maybe say the area between the curve and the x-axis is 4 here. But it's going to integrate to be 0 because this is a -2 in some sense with the signed area because it's below the x-axis. Adding up little rectangles here with negative heights is going to be adding up negative valued areas. So they would be canceling with these positive valued areas. So if I want to find the total area here, I have to find places where it crosses from above the x-axis to below the x-axis. And then if I wanted that total area, I would have to integrate from 0 to pi, sine of t dt, plus the area from pi to 2 pi of negative sine of t dt, because I want to change these things into these things. So I flip it over on the parts where it's negative. So be careful if it's asking you to give a total area under or between a curve and the x-axis, that type of thing, that you're going to need to find roots and then do 2 different integrals based on where your roots are. So let's do some example problems. Just evaluate the integral from 0 to 2 of x minus 3 dx. Okay, so I'm going to multiply this out to sort of simplify things. 0 to 2, x squared minus 3x dx. I'm going to find an antiderivative. The antiderivative of x squared is x cubed over 3. The antiderivative of 3x is 3x squared over 2. And then what I do, I found the antiderivative here. This is the antiderivative bit. Then I put a vertical bar, which tells me that I need to evaluate. And then down here, I put x equals 0, and up here, I put x equals 2. So I'm going to evaluate it at x equals 0. I'm going to evaluate it at x equals 2. I'm going to take the bottom one minus the away from the top one. So the top one minus the bottom one. So this will be equal to 2 cubed over 3 minus 3 times 2 squared over 2. That's the evaluate at the top bit, minus. I'm going to evaluate at 0, which is 0 cubed over 3 minus 3 times 0 squared over 2. And that's the evaluate at the bottom bit. There's the difference. Top bit minus the bottom bit gives me the entire area. So that's going to be 8/3 minus 12/2. So that's 6. And then these both evaluate to be 0, so minus 0. So that's going to equal 18 minus 10/3. Because this is 18. Sorry. No, that's not right. Yeah, it is. This is 18/3. 8/3 minus 18/3 is minus 10/3. Questions on that one? Online folks still doing okay? Okay. Let's do this guy. He looks interesting. 1 to 8. X to the 1/3 plus 1. X to the, no, sorry, 2. 2 minus x to the 2/3 divided by x to the 1/3. How am I going to find an antiderivative for this? It's a bit of a mess right now. What can we do first before we start looking for an antiderivative? Yeah, we're going to do algebra to simplify things first. So we're going to expand it out, multiply it out, and then divide by that x to the 1/3 in the denominator. And since that's just a monomial down there, everything is going to be sort of polynomial looking, and we can go from there. We're about done. So this is the integral from 1 to 8. We'll expand that out. I'm going to have 2x to the 1/3. I'm going to have a minus. So I'm taking x to the 1/3 times x to the minus to the 2/3, which is just x to the 1. So minus x. And then I've got a plus 2, and I've got a minus x to the 2/3. If I FOIL that all out, and then I've got an x to the 1/3 down here, dx. So I'm going to take away a third factor of x from each of the terms in the numerator. So I'm going to integrate from 1 to 8 of 2, because x to the 1/3 over x to the 1/3 is just 1, minus x to the 2/3, plus 2x to the minus 1/3, and then minus x to the positive 1/3 dx. I can take antiderivatives, so it's going to be a 2x. I'm going to increase the exponent by 1, so that's going to be a 5/3 divide by the new exponent. I got 2. That's a minus 1/3, so that's going to increase the exponent to a 2/3 divide by the new exponent. Got a minus, increase the exponent by 1, so that's 4/3 divide by the new exponent. Put my evaluation bar. I'm going to evaluate at x equals 1 and 8. So we'll plug 8 in, and I'll get 16 minus 3/5 of 8 to the 5/3. A third power of 8 is 2. 2 to the 5th is 32. Plus I've got a 3, because the 2's cancel, times 4, because 8 to the 2/3 is 4, minus 3/4 times 2 to the 4th is 16. Okay. Then minus, I evaluate all this stuff at 1. That's going to be 2. This is just going to pull off the coefficients, minus 3/5 plus 3 minus 3/4. So I'm going to have 20ths, it looks like, because I got a 5 in the denominator and a 4 in the denominator. So everything in terms of 20ths is going to mess things up a little bit, but that's okay. So 16 minus 96 over 5 plus 12 minus 16 over 4 is 4, so that's minus 12. That's nice. Those cancel. Minus all of this stuff, which is going to be a 5 and a out of 20ths. That's 12 20ths, and that's 15 20ths, so minus 27 20ths. To turn that into 20ths, I'd have to multiply by 4. So that's 16. Multiply that by 4, I get 384 over 20 minus 5 plus 27 over 20. 11 minus 84 minus 27 is 57. 357 over 20. 220 over 137 over 20. As long as my arithmetic was right, we're good there. Okay. So that's just some basic evaluation of integrals. Let's see one of these things, which are kind of interesting. So I want to find the derivative with respect to x of the function 0 to the square root of x cosine of t dt. Okay, the whole idea before was if I have the function f of x equal to the integral from a to x f of t dt, then f prime of x equals f of x, right? I don't have just an x up here though, right? So I'm going to have to put this together so that I can use this context. So we define f of x, well, let's call it f of g because I'm going to use a chain rule here. Define f of g equal to the integral from 0 to g cosine of t dt. Then this thing here, this is equal to f of the square root